Welcome to Refrigeration Cycles. Today, we're diving into a critical topic in Thermodynamics 2, refrigeration cycles. This chapter focuses on systems that move heat from cold spaces to hot spaces, enabling everything from home refrigerators to large industrial chillers. Think about how vital refrigeration is, keeping food fresh, preserving medicine, and supporting industrial processes. Understanding these cycles helps you see the hidden energy flows all around you. By the end of this session, you'll be able to explain how refrigeration works, calculate performance using COP, coefficient of performance, and understand why no fridge is ever 100% efficient. Let's begin. 1. Introduction to refrigeration and heat pumps. Let's start with the basics. Refrigeration is all about moving heat from a cold area to a hot area. That's why your fridge feels warm at the back, even though it keeps your food cold inside. The device that does this job is called a refrigerator, and it follows a specific set of steps we call a refrigeration cycle. The most popular one is the Vapor-Compression Cycle. It's the workhorse behind almost every household refrigerator and air conditioner. But there's also a close cousin, the heat pump. It uses the same process, but instead of cooling your food, it keeps your house warm. So whether it's keeping your ice cream frozen or your room cozy, it all comes down to understanding these cycles. Number 2. Focus on coefficient of performance, not just efficiency. When we talk about refrigerators or heat pumps, we don't use the term efficiency. Instead, we use something called the coefficient of performance, or COP, because these devices move heat, not just convert energy. For refrigerators, COP is the heat removed from the cold space divided by the work input. For heat pumps, it's the heat delivered to the hot space divided by the same work input. And here's a useful shortcut. The COP of a heat pump is always 1 unit higher than that of a refrigerator under the same conditions. Simple, clear, and practical. COP helps you instantly tell how good your refrigeration cycle is. 3. Understand the ideal, but don't chase it blindly. The Carnot cycle is famous because it represents the highest possible efficiency for any cycle working between two temperatures. But here's the catch. It's like a perfect fantasy. It looks great on paper, but is almost impossible to use in real life. Why? Because it needs perfectly isothermal heat transfer and compressing two-phase fluids, which is practically unworkable. The equations are simple. For refrigerators, COP depends on how cold the low temperature is. For heat pumps, it depends on how hot the high temperature is. But real systems always fall short of Carnot's perfection. So study the Carnot cycle for understanding the limits, not for designing real machines. 4. Break it down into simple, powerful steps. The ideal vapor compression refrigeration cycle isn't complicated when you split it into just 4 simple steps. First, isentropic compression. Think of it like pumping up a bicycle tire. You squeeze the refrigerant, making it hotter and raising its pressure. Next, constant pressure heat rejection. Here, the hot refrigerant dumps heat outside like a hot drink cooling off. Third, throttling. Imagine quickly opening a valve. The pressure drops fast, and so does the temperature, without any useful work. Finally, constant pressure heat absorption. This is the magic moment where the cold refrigerant soaks up heat from your fridge or room. 4 clear steps, each with a role, creating an efficient, repeatable cycle to move heat where we want it. 5. Real cycles aren't perfect, and that's okay. Textbooks love to show ideal cycles, but real-world refrigeration is messier. Machines aren't perfect, and irreversibilities make sure of that. In real systems, compression isn't isentropic. You lose extra energy in the compressor. Pressure drops happen as refrigerant flows through pipes and valves. Heat leaks in and out of the system because no insulation is perfect. Plus, you get subcooling and superheating, tiny tweaks that can either help or hurt performance. The key takeaway? Every real cycle will always fall short of ideal performance. Your job is to understand these losses and minimize them, not to expect perfection.
6. Go beyond energy. Focus on quality with the second law. Energy doesn't tell the whole story. Second law analysis looks deeper, measuring not just how much energy you use, but how wisely you use it. That's where second law efficiency comes in. It compares your system to the best-case scenario, the Carnot cycle, showing how close you really are to ideal performance. Even more useful is exergy destruction. It tells you exactly where your system wastes useful energy, whether it's in the compressor, condenser, or elsewhere. This is your roadmap to improvements. Find the biggest exergy losses, fix them, and you'll get closer to optimal performance.
7. Choose refrigerants with a balance of performance and responsibility. Choosing a refrigerant is more than just picking what's coldest. It's about balancing performance with safety and environmental impact. You want refrigerants with great thermodynamic properties like high latent heat and low boiling point to maximize efficiency. But you also have to watch out for environmental damage. Older refrigerants like CFCs and HCFCs harm the ozone layer. So we now use HFCs like R134A, R410A, and R32, which have zero ozone depletion, but they still contribute to global warming. Then there's toxicity and flammability. Ammonia is super efficient and environmentally friendly, but can be dangerous. Your job? Select refrigerants that give you performance without compromising safety or sustainability.
8. Match the heat pump to the situation. Not all heat pumps are created equal. Choosing the right type depends on your environment and budget. Air source heat pumps are the most common because they simply grab heat from the outside air. They're easy to install, but struggle in very cold weather. If you want higher efficiency, water source or ground source heat pumps are your answer. They tap into more stable temperatures underground or in water bodies, but they cost more upfront. And remember, when it's freezing outside, even the best heat pump needs help. That's where supplementary heating comes in to keep things comfortable during the coldest days. 9. Boost efficiency with smarter refrigeration designs. Basic vapor compression cycles are good, but advanced systems can make them great. Cascade refrigeration systems use multiple refrigerants in steps, like a relay race, to achieve much lower temperatures, perfect for things like ultra-cold storage. Multi-stage compression with intercooling breaks the compression into smaller steps, cooling the refrigerant in between. This cuts down on compressor work and energy use. Flash chambers add another clever trick by removing excess vapor after throttling, meaning less vapor goes through the compressor. The result? A smarter, more efficient refrigeration cycle that saves energy while delivering better performance. 10. Understand when gas refrigeration makes sense. Not every refrigeration system uses liquids. Sometimes we use gas. Gas refrigeration cycles are built on the reversed Brayton cycle, where there's no phase change, just compressed and expanded gas. You'll see these systems in aircraft cabins and cryogenic applications, where simplicity and lightweight matter more than efficiency. Yes, their COP is lower than vapor compression cycles, but they have fewer components, making them ideal for aviation and high-tech cooling. Regeneration, where exhaust heat is reused, helps boost their performance, squeezing more cooling out of each cycle. 11. Use heat instead of electricity when it makes sense. Absorption refrigeration systems break the usual rule. Instead of mechanically compressing refrigerants, they use heat, especially low-grade heat sources like waste heat, solar, or geothermal energy.
The trick here is simple. A working fluid like ammonia gets absorbed into water, and heat drives the separation and circulation, skipping most of the compressor work. Yes, absorption systems are less efficient than vapor compression systems, but when cheap or free heat is available, they can be the smart, sustainable choice. It's about using what's already there instead of relying on electricity.
12. Simplicity at a cost, the thermoelectric trade-off. Thermoelectric refrigeration is all about simplicity. It uses the Peltier effect, where electric current directly moves heat from one side of a material to the other. No compressors, no moving parts, and completely silent operation. That's why you see it in mini fridges and portable coolers. But the trade-off is efficiency. Compared to traditional refrigeration cycles, thermoelectric systems have much lower efficiency. So they're great when you need simplicity and silence, but not the best option when energy efficiency is your priority. 13. Master the essentials with these core formulas. Let's wrap it up with the key formulas you'll actually use. First, the COP, coefficient of performance, shows you how well refrigerators and heat pumps perform. Remember, the heat pump COP is always one higher than the refrigerator COP. Next, we have the Carnot COP, which tells you the theoretical maximum performance based only on temperature limits. The second law efficiency compares your real system to this Carnot limit, great for diagnosing performance gaps. Finally, exergy destruction shows where useful energy is wasted, helping you pinpoint inefficiencies. These formulas aren't just math, they're practical tools to evaluate and improve real systems.